Both of these we can consider perfect squares because they're squared. Now, if we think about the shape of this, x plus 3 squared, remember this means x plus 3 multiplied by x plus 3. So if we were building this with tiles, we'd have an x length, x times x. We'd have 3 x's here, boop, and we'd have 3 x's here. I'm just going to fill this in. There's my 3 x's. There's my 3 x's. And notice in here, in this region right here, I have 9. Right? So if I were to multiply this out, I've got an x squared plus 1, 2, 3, 4, 5, 6 x's plus 9. This is a perfect square because I can arrange all those pieces into a square, right? This length is equal to that length, and I can write it that way, x plus 3 squared. Similarly, x minus 5, I'm not going to draw out all the tiles. I'm just going to kind of do the generic one. This would be x minus 5 multiplied by x minus 5. So we've got x squared, minus 5x is there, minus 5x is there. And notice in this bottom right corner, negative 5 times negative 5, we have 25, right? So this would be x squared minus 10x plus 25. So now take a second and notice, we've talked about this in class quite a bit. Notice the relationship between this, and that. Oops, sorry. So notice that 3, when we multiply this out, got doubled in that middle term, right? Because there's 3 of them here and 3 of them here. And that 9 is 3 squared right here. In other words, if I take half of this middle term and I square it, I get that n term. So that helps me think about the structure of these. So if I had something that looked, say like this, x squared plus 8x plus 16. If I start to recognize that structure, let's see, half of 8 is 4. 4 squared is 16. That means I could make this square x by 4, x by 4. There's my 16 right there, right? So this is equivalent to x plus 4 squared. So with that in mind, and again, we've practiced this a lot in class, let's complete the squares on these. Let's think about like, what would this term be to turn this into a perfect square? Well, I've got 4 x's I need to distribute. You know, if I draw it, I've got my x's, and 4, I need to cut that in half, right? Because I need 2 of them here, 2 of them here for 4 total. What would go here? 4. So that would be plus 4. And then I could write this as x plus 2 squared, right? X plus 2 times x plus 2. How about this one? Negative 8. Half of negative 8, let's see, that's negative 4. Because my square would be like x negative 4, x negative 4, negative 8 is right there. What would go here? Negative 4 times negative 4, positive 16. So if I add a 16 into here, this would be the square x minus 4. Half of 5? 2.5. 2.5 squared, you could grab your calculator or whatever it would take. We get 6.25. So this would be x plus 2.5 squared. Now this act of like figuring out what goes here and putting it here, we call it completing the square because we're adding something to it to make this into a square, to like complete it so it's a square. So this idea of just kind of arbitrarily adding something in, let's clean that up a little bit. So if I had something like x squared plus 4x plus 1, and I was asked to complete the square on this, notice I have a plus 1 here. Like if I think about what I have an x squared, so x times x. I've got these 4 x's. I'm going to cut those up into 2 and 2. So there's my x squared, there's my 2x, there's my 2x. And I need 4 in here, right? But I only have 1. So there's a couple ways to think about it. One way to think about it is I need 3 more, right? So basically I'm 3 short. In other words, if I said I had this square there would be 4 in here, but I only have 1, so I'm 3 short. So what I'm saying is this collection of tiles is equal to this square, if it was all the way filled in, minus 3. Now there's a real mechanical way to do this, right? Which is to go like, let's see, x squared plus 4x, and I'm put this 1 out here. I'm just going to complete the square here. So half of 4 is 2. 2 squared is 4. So I'm going to add 4. So notice when I add 4, though, I've made this whole thing 4 bigger than it was. So I have to balance it out by subtracting 4. Again, I'm adding 0, right? Plus 4 minus 4. But I did that, so then this part right here, that's a square. I could write that as x plus 2 squared. And then I have 1 minus 4, and I have 3. I'm 3 short, right? So this collection of tiles is 3 short of that perfect square. Let's do another one. Same idea. I'm going to push that 7 out. So let's see. Half of 4 is 2. 2 squared is 4. I'm going to add 4. And I got to subtract 4, right? Balance it out. So that means this part, x plus 2 squared, 7 minus 4 is plus 3. In other words, this collection of tiles is this perfect square, right? Notice I've got 4 in here with 3 left over, right? Because it has 7. So that is equivalent to that. Let's try a couple more here. Let's complete the square on this. I'm just going to shove that 9 out here a little bit. Half of 8 is 4. Square that is 16. I've added 16, so I've got to subtract 16. You see how 9 would be 7 short, right? This part, that's my square. X plus 4 squared. 9 minus 16, that's negative 7. Right? I could fill in, what I had originally was 9. I could fill in 9 of these spots, I'm 7 short. So this collection of tiles, x squared plus 8x plus 9, is 7 short of that square. Another one like this. Half of 8 is 4. Square that is 16. I added 16. Bookkeeper comes in, it's like you got to subtract 16 because we want it equivalent to this. This is a perfect square, x plus 4 squared. 25 minus 16, I think that's 9. We had 9 left over. Yeah, this is 9 more than 16. So this square plus 9 is the same as that collection of tiles. Last one I'll do. Half of 10 is 5, squared is 25. I added 25, so I need to subtract 25. I'm already 3 negative, right? And I need 25. So that means I'm actually 28 short of the square. There's my square. X plus 5 squared minus 28. This collection of tiles is that square minus 28.